Hello, everyone. Thank you for being here. Today I will discuss the research that I've been doing on developing new benchmark datasets for the resource-constrained multi-project scheduling problem. The outline is as follows. I will first discuss the existing research, then I will discuss the new summary measures that we developed, then I will go over the datasets that we generated and how we evaluate them, and last of all, we will evaluate whether these datasets have an impact on the performance of solution algorithms. So first of all, in previous research, we implemented an existing, we re-implemented the generation procedure of Browning and Yassin, which generated datasets for the multi-project scheduling problem. We made some small adaptations, and based on this procedure, we were able to generate new datasets. However, we observed that there were some shortcomings to the existing approach. First of all, we were not able to determine what is the feasible range for each of the parameters. For instance, for the NARLF, here you see it goes from -30 to +3, but there are no theoretical indications about whether these are actually the extreme values or bounds on the values. So this was the first shortcoming that we observed. Second, we observed that there are interdependencies between several parameters. For instance, here we generated datasets with 6 projects, 12 and 24. And these figures show that each dot is an instance that we could generate with a specified value for these 2 parameters. And as you can see, the feasible range of the NARLF values reduces when there are more projects. Also, the feasible range for the utilization factor on the y-axis increases, as you can see. So this becomes a problem if you want to try to do a full factorial generation, because not all combinations will be feasible. The third gap that we identified is that the existing measures describe some of the relevant characteristics of the project, of a portfolio, but not everything. Some measures are lacking. So in our new research, our objectives are as follows. We want to define new summary measures that are able to describe a wider range of characteristics for the portfolios. Second, they have a clearly defined range of feasible values. And third, the different parameters are as independent of each other as possible. When we have the summary measures, we then will want to generate new datasets and also evaluate whether these datasets actually change something for solution algorithms. So first, the new summary measures. Before I discuss them, I will shortly show you the alpha measure because we use it a lot in this research. The alpha measure is an indication of how varied the different values are. So it's a bit like a standard deviation or a variance. And as you can see here in this example, the alpha variation equal to 0 means that all values are equal or as equal as possible. So in this case, we have 4 values of 3, indicating an alpha value of 0. Suppose that we have an upper bound and a lower bound on each of these values equal to the upper bound equal to 5, lower bound equal to 1. Then this is the most unequal distribution, and then thus this has a value of 1. So using this, this measure, we can generate a lot of different variation types, going from equally distributed to the most unequally distributed that's possible. So then I will now discuss the 3 types of summary measures. The first type describes the basic characteristics of the portfolio. These are the characteristics, let's say, that we already observe in existing data sets. First of all, we have the number of activities per project. We also have an indication of the network structure. For this one, we use the SP indicator, which indicates how serial or parallel a project is. And third, we have the independence strength, which indicates how tight is the resource availability. I will shortly explain them by an example. Here we have a portfolio of two projects. Each of the projects has a size, so we can calculate an average and also an alpha variation of it. The same for the SP indicator. So project 1 is more parallel, project 2 is more serial. So we take an average, also an alpha variation. And for the independence strength, I will explain this a bit more in detail. It looks at the maximum demand over any independent set in the whole network. So for project 2, the maximum demand over an independent set, you can see here is 11. For this project, it's 9. So in total, it's 20. Any demands, so if you reset this resource availability to 20, any precedence feasible schedule will never be resource constrained. So this is an upper bound on the relevant values for the availability. On the other hand, the minimum value for the availability in this case would be 8. If it would be lower than this activity would not be cannot be executed. So we calculate these two extremes, and then for this case we check what is our availability, 10 in this case, and we see where in this range of feasible values does it occur, which leads in this case to an independence strength of 0.16, indicating quite tight resource constraints. In our example, we don't calculate an alpha variation because it's calculated over the different resource types, and we only have one resource type here. But in realistic instances, we also can calculate an alpha value. So the basic characteristics consist of these 6, and then we have the network characteristics. We allow inter-project precedence constraints. So some projects can start after other projects, and more specifically, we allow 2 types of precedence relations between projects. First case is going from an activity in one project to the dummy start of another activity. So it's a bit like a milestone. If a part of a certain project is finished, then we are allowed to start on a new project. Also the other way around, there can be a precedence relation from a dummy end to somewhere an activity in another project, indicating if we finish this project completely, we can start this segment of another project. Using these relations, we can look at 2 different properties of the new multi-project network. First of all, how serial or parallel is the complete portfolio, and second, how tight are these inter-project precedence relations. I won't explain all the details, but I will show you the intuition. So here we have 4 projects, and each project is represented by a segment indicating the length of the project, which is the longest chain of activities that we can find in the network. So if all activities would be in parallel, the length of the portfolio would be 5. If all projects would be in series, the length would be 14. So these are the extreme values for the portfolio length. And in our example here, the length is 8, as you can see, due to this precedence relation. So we measure this and we compare it to the extreme values, and this gives us an indication of how series or parallel is our portfolio. The second measure is the float of the multi-project, and this gives an indication of how free are the projects to be executed at any time. In this case, project 1 and 2 cannot be started earlier or later, because then they would change the length of the portfolio. However, 3 and 4 can be started later, so they have float. And the more precedence relations we add to the network, the lower the float will become. So in this case, only project 2 still has freedom in execution. And in this case, all projects, none of the projects has any freedom anymore. So here the multi-project float will be 0. We also, we specify what is the maximum value. So we always obtain values between 0 and 1. Then for the resource characteristics, in existing data sets, most of the times resource types are either completely shared by all projects or dedicated to one specific project, but we also want to allow all possible cases in between, where an activity, a resource type is assigned to some projects, but not all of them, for instance. So to do this, we require two matrices, which indicates how resource types are allocated to the projects. We have a binary one in which, a binary one in which a 0 indicates that, a 1 indicates that project 1 requires resource type 1. So some of its activities have a demand for resource type 1. And the fractional matrix indicates which percentage of activities of this project requires this resource type. So this can only be a non-zero value if this value is equal to 1. So the first summary measure that we define is the resource sharing ratio, which actually measures the density of the fractional matrix. At most, it can be 1 for each position in the matrix. So that's our maximum value. And we specify a minimum value, which is each resource type should be required by one project. So there should be, the sum of the matrix should be at least equal to the number of resource types, which is K. Based on this, we can calculate the density of the matrix. Higher density means the resources will be shared more among the projects. However, this density does not describe the structure of the matrix. So we require two additional parameters, the resource dedication and the project dedication, which look at the row and column sums of the binary matrix. Resource dedication, if it is low, it means that the resources are quite equally distributed over all projects, which in this case, most equally distributed it can be is 2, 2, 1, 1. The higher this resource dedication, the more unequally distributed these resource types become, which results in more projects, more resource types being completely shared among all projects, like here, and more resource types being completely dedicated, so only used by one project. So the higher this becomes, the more we go to the standard case where all resource types are either shared or dedicated. We can do the same for the row sums. So a low project dedication means that all projects have a similar number of resource types that they require. The higher the project dedication means some project types will require a lot of resource types, and some projects require almost none, as you can see here. So based on these characteristics, we develop new data, or we generate new data sets. So our generation procedure looks like this. First, we read in single project networks based on the specifications for these values. Then using these networks, we create a portfolio network, which is specified by these values. Then we generate the resource allocation matrix, which is specified by these parameters. And last, we determine the resource availability, which is determined by these. So we developed four data sets with our generation procedure. The first one only contains the basic characteristics. So this is actually quite similar to existing data sets. In the second, we added multi-project network characteristics. And the third one, we only focused on the resource characteristics. And then the last one, we combine everything. As I'm short in time, I will go over these slides and shortly discuss what is the impact on the performance of solution algorithms. So we tested a lot of priority rules on previous data set from previous research in our new sets. And we see that from the top 10 performing ones, only 3 are the same. So this means that by introducing these new characteristics, new priority rules become interesting, which also means that this is also interesting for meta-heuristics because other ways of looking at the problem or prioritizing certain types of projects may be beneficial. And last of all, we also implemented the genetic algorithm and looked how well is the improvement of a genetic algorithm over the best performing priority rule. As you can see, this performance is relatively high for set 1 and 3, but for set 2 and 4, where we added inter-project precedence constraints, the performance deteriorates, which means that further research is required for these data sets. So the existing operators in meta-heuristics are not sufficient to solve instances where there are inter-project precedence relations. So this would be an interesting opportunity for future research. Thank you for your attention. If there are any questions, I will be glad to answer them.